already stated, he's going to be presenting single program, multiple data, IR, a parallel programming model unifying dialects. And yeah, then we're going to take questions as well.
Yeah, thank you very much. Yeah, as said, my name is Semih. I'm from Aachen. Actually, we realized when talking to Ege, it's my last day of my 4th year of PhD, so I have 2 more years. But everything is fine, so I'm just going to stay schedule. So yeah, let's start. It's about SPMD IR.
Doesn't switch. Okay.
So basically, it's about HPC systems. You know, like nowadays we have data clusters, we have different systems, and we actually they're getting more complex. Not only the hardware but also the software. And for effectively utilizing them, we are using different parallel programming models, such as MPI. We have also like Nickel, we have SHMEM and vSHMEM, for example, from NVIDIA. We have also AMD alternatives. Maybe question, has anyone not used any of them? Can you raise your hand if you have never used MPI or, okay. So basically these are parallel program models, so they are like giving you a function call saying, okay, here you have this array, please send this to the other process sitting in another compute node, basically. And you have all kinds of utility functions, but basically it's just for communicating data, mostly. Okay, so and the conventional approach is that we have different tools. For example, we have a tool analyzing your program. We have a tool optimizing your program. But these tools are often written only for one parallel programming model, let's say for MPI. And some tools are supporting multiple of them, but they have their internal abstraction. So if I want to have or introduce a third tool, I would need to re-implement all the different functionality. The idea here was to introduce an intermediate layer and include the abstraction into it, so what I call SPMD IR. And so tools working with SPMD IR should automatically support all the program models which are lowered or lifted to my SPMD IR. So the initial problems was that, as I mentioned, tools are developed for individual models or incorporates abstraction. And so basically, let's say MPI, there's always a specification for the program model. Like MPI has like 1,300 pages of a specification, for example, and the other ones are also not really short. So basically, there are lots of information here, so how the runtime is actually doing stuff. But the compiler does not know anything about that. They just see a function, and maybe you can see, okay, here's a const, here's not a const, and that's it. But we could give the compiler much more information, so you can apply certain optimizations. So the key feature or the ideas of the SPMDIR is that, so instead of having, like let's say, like lots of MPI functions, so we have a MPI send, we have an ISend, which is like a non-blocking one, like asynchronously, we have a buffer, so lots of different variations, let's say 20. And instead of having 20 operations which are like from essentially the same, we just have one and then use attributes for differentiating them. Secondly, we want to enrich the semantic information, so we have typed operands and results. For example, we use basically integers for IDs for the process ID. We have memory for LLVM pointer type for the communicated data, and we use custom dialect types for the remaining. Let's say we have a communicator, which is basically like a group of processes. And for this like special entity, we use a custom type. And we will see in a later slide why this is important. Secondly, we want to enable a generalization. So by unifying different program models into one layer, we enable like different approaches working with them. Then we want to specify the side effects. So even so, sometimes like you have like this const at your API definition, they are sometimes lost along the way through the compiler. So specifying really the side effects in our dialect in MLIR will make sure that that the compiler will know, okay, here I need to make sure there are there are some side effects, but we can also additionally define custom resources. So we could also reflect the side effects happening in the runtime. So for example, if they are creating some data structures in the runtime, and for example, there are also functions for freeing them, you could track that. Yeah, and we can also define categories, also called traits in MLIR, which is quite useful for the analysis. And then there's another component which we call like extended MV analysis, multi-value analysis. Multi-values are quite important in SPMD programs. Multi-value is when a value is not the same for all processing elements or units. So yeah, we can also derive certain other information by it. I will skip it for now. So the remaining of the talk, I will give a bit of a background on MLIR and talk then about the SPMD, the workflow, gives talk a bit about the use cases, yeah, and then also some, let's say, lessons learned and so on from myself. So with MLIR, who has never used MLIR or heard about it? One person, okay. Okay. So I will make it quick, but still give the most important parts here. So an IR is a representation of the source code serving a certain purpose. And MLIR is an IR and compiler framework building upon part of LLVM, published 2021, I guess. And here we see that yeah, we have not only one IR, we have lots of IRs, so they are always transformed one to the other. We apply analyze on them, we are verifying stuff, we are optimizing. We could derive a report from that. We could also generate machine code, run the code actually. And yeah, we want the IR can facilitate optimizations, makes passes reusable and extensible, and we want to ease lowering to machine code. And if you compare LLVM IR with MLIR, we could say it's more extensible, reusable. We can mix low-level and high-level abstractions, and we can encapsulate domain-specific semantics in form of dialects, which is a collection of custom operations, types, and so on. And the idea here was that, okay, we have SPMD, relate information, and we want to express it in our own dialect and a set of IR constructs next to other special purpose dialects. And here a quick look at also one use case and also giving a running example in MPI. So here we have MPI. It's really a simple example. So MPI com_rank gives us in our process group communicate a rank ID. And then we, yeah, here we start like an array epoch, it's called, but basically we say, okay, here, from here, we have one-sided communication. So rank 0 is putting data, which is in buff, to the target, which is here described by with a window. And here in the fifth line, we have a data race. So because this is one-sided communication, which is not completed immediately. This communication is completed here when the second MPI wooden fence is called. So we should not touch buff until this is called. But here it is, so we have a data race. So if two units of execution access concurrently the same memory location without proper synchronization, and at least one of them is a write, then this leads to undefined behavior, and we should avoid it. And there's, if you go to details, there's local and remote completion, and also local and remote data races. But here we look at local data race, so really at the site where the communication is initiated. So quick on MLIR. So basically we could get this code. We are looked the example to MLIR, and here with red we highlight the dialects, with orange the values, and blue the types. And here I just want to make clear that in MLIR we have a dialect for everything. So we have a function dialect for function-like behavior, where we can call functions. We have, for example, the arith dialect, where we have arithmetic operations, for example, this compare operation. Then we have the STF, structured control flow dialect, for having a control flow operations. Here's the if. And yeah, this is the main message basically I want to show here on this slide. And all of these dialects can seamlessly interact with each other. So MLIR provides a toolset to develop an expressive IR composed of multiple levels and semantics. And here also we see that, for example, here we have not only the high-level dialects, we could also use the LLVM dialect, which would be kind of low-level. However, just getting to MLIR does not solve all problems. Yeah? So for example, here, like if you look at the MPI or let's say program model view, for example, the world, we have hidden semantic information because this is an entity which is quite important for our analysis, but in the end it's just represented as an integer. So the compiler does not know anything about how important this is, just an integer. In MPI, there's quite recently there's ABI standardization, so the different implementations. So there's not only one implementation of MPI. So there's one from Intel, there's one from maybe the community and so on, like MPIG. And they might implement this communicator differently. Now, after the standardization, all of them have to say, okay, the word communicator is 0, but it's still an integer. It's not like a special type. Then we have no dedicated types. We have no dedicated values. We have no dedicated operations. The memory set effects are not clear. We don't have any traits which are grouping different functions. And we also don't know anything about the runtime effects. And to tackle all of that, we define an SPMD dialect in MLIR. So here, if we go from source code to default MLIR and then to the SPMD within MLIR, yeah, it's quite a lot maybe on the slide, but basically what I want to show is that we define for the different function calls. So previously we had like this MPI comRank call. Now we have an operation which is called comWorld, which gives us a comWorld, let's say constant-like entity, which is of type SPMD com. The same is exactly the getRankIncom, which is this MPI comRank. But except the SPMD, like all the operations which we transform to that, the rest of the IR stays the same. So we can still use the other dialects like STF and so on. Further, we also see here that we applied the multi-value analysis. So we also know for each operation whether it's executed by all processes, for example. Here we say, okay, this is just in the main, it's executed by all. Here within the if branch, we say, okay, we know statically that executable only is 0. And from the scope, yeah, we can, like for example, MPI and the other program models, we can divide the different function calls in categories, like management of processes, communicator, memory, and so on. We have communication functions. For all of that, we defined the operations in the SPMD dialect, and we tried to have a minimal set. So we always try to map something to the existing ones before we introduce something. But if something is only given in one program model, let's say we have only device stuff in nickel and not in MPI, then we would introduce it anyhow. So I will not go over all of the operations, but just that you see, okay, for example, for synchronization stuff, we have a wait function. For communication, we have a send and receive, we have a broadcast, and so on. We furthermore define traits. So we have, for example, a collective trait which says, okay, this operation needs to be executed by all processes in the communicator. And we also define resources like what's happening in the runtime part. And for the workflow, yeah, we start in C++. We are supporting currently MPI, SHMEM, NICL, and NVSHMEM. Where this is transformed first to LLVM IR and then lifted to common MLIR. Yeah. And after that, let's say the main SPMD IR toolchain starts, where we have a transformer component which transforms one program model to the SPMD operations. And then we apply the extended multi-value analysis to really have everything we want in our final SPMD IR. And this we can forward to static tools, for example, for verifying the collectives, data arrest detection, and maybe even performance optimization. And what I was working recently, we support now also NVSHMEM, GPU kernels, GPU initiate API calls. We actively use now the traits, so we no longer say, okay, if this operations encounter does do this, we just say, okay, use the traits. So if, and this happens a lot that program model introduces new functions, then our analyzer should not break. Currently, we use the enzyme reactant frontend for C++. This is kind of like a bigger project which subsumes also the work like Polyguys did. I think some of you know it. Because currently there is not like a real official C++ frontend in MLIR. There are like the Clang IR, which is currently in development. But yeah, currently we switched to it, and I'm quite happy right now. And I'm porting existing analyzers to MLI's data flow framework and remove certain limitations, for example, inlining everything. And furthermore, we have now the generic op creation through the integration of machine readable program model specifications. So as I said, for example, MPI has like over 1,000 pages of specification. And if we don't have some kind of machine readable interaction with that, we would need to implement the knowledge of it into our tool. And to reduce the amount, we try to reuse like this machine readable specification in our parsers. And we also have ongoing work to also support OpenMP. And as everything is a research project, it's not really about, okay, we can perfectly getting OpenMP in align with other program models. It's more about, okay, where are the limitations, how far can we get, and so on. The first use case is here, the collectives verification. So the standards say the same kind of collectives, for example, broadcast, has to be called in order for all processes of the same communicator. So in this example, here's the entry. Then here we have a barrier in this branch. Here we have a barrier. And here also we have a barrier. And if you know, say, and we can text to the C, they are like aligning, but this is not aligning with them. So if now the branch is multi-valued, which means that all processes are not taking the same branch, because the value they are depending on is different or may be different for them. So we can say one process is, for example, going this path, some is going this path. And what this means is that they are waiting here, that the other one is going into the barrier. And since they have two barriers, in the end it will go to a deadlock because they are waiting off each other. There's another tool called ParCouch, which I always use for comparing myself to it. And essentially they are working on LLVM IR, I'm working on MLIR, and we applied the approach of them onto MLIR with some extensions. I will not go over it. We are using traits. For example, they are maybe using the different API codes directly, but I just use the trait, okay, we have collective, so if I want to add a new operation, my analysis should still work. Yeah, we have a micro benchmark suite. We port different codes to the different program models. You should know, like MPI is, for example, like really a standard program model. It's like used maybe 20 years, 30 years, I don't know really. And it's and the other ones are a bit new. For example, Nickel and so on, they're like 5 years maybe, and are mostly also used in the AI machine learning area. So that's why lots of code, lots of benchmarks are given an MPI, but we don't have so many in the other program models. So that's why we also need to port them for the comparison. The second use case is data race detection. We saw the example previously. I will not go over how we do it. Just as a comparison, we are more extensible. Like if you compare our tool with ParCouch, we can say we are more extensible through the unification layer, which is mostly our selling point. We are API call independent using traits. We coupled it with extended multi-value analysis to even increase our accuracy. And this is a more detailed thing. We don't only support one-side communication or another category. We also support the interaction of them. and which is really, yeah, let's say, pleasing in our dialect is that since we get all of the program models into one layer, for us it's not really more difficult to support multiple program models. For example, for a tool, it's really difficult to say, okay, I have MPI, I have nickel, I also want to support a program which uses both, or maybe use 3 program models. But since we get everything into one layer, this is the same for us nearly if you just have one. So here we I try to give a really simplified overview. There's also another tool. It's also developed by us. It's called MAST, but it's a dynamic tool, so it happens at runtime. Yeah, exactly. So the tool. So if you say, okay, do we have an abstraction? In SPMD, we have an abstraction which is happening at compile time. Parquet does not, and MAST is only an RMA specific one. Yeah, these are the program models. Yeah, try to go a bit fast on it. So basically, we have certain achievements through the unification. So we don't only support one category, we support multiple categories, also mixing of CPU and GPU codes. And yeah, we have lots of artificial use cases, or let's say test cases to see if we can do it. And yeah. And yeah, there are, but so basically they are like always like from the tool sides, they are like static tools, like at compile time, and those at runtime. And both has a advantages and disadvantages. So for I think here also on the slide, yeah. So a static tool has a problem with aliasing, yeah. And through aliasing, we always need to be conservative, and that's why we end up in false positives. Yeah, false positive is that there is no error, but we say there is an error. So falsely saying here is something wrong. However, the static tool is independent of actual control flow. We have, let's say, not a big overhead. It is scaling and no interaction. A dynamic tool has no problem with aliasing, but it is dependent on the actual control flow. So if the actual program you are observing is not going through the path that has the error, you will never find it. So you have a false negative, and you might end up in higher overhead because you basically scale with the runtime and maybe add like a 10x to it. And the idea we did here also was to combine a static tool with a dynamic tool, forwarding the error report from our tool to the dynamic tool. So the dynamic tool can, yeah, so I think here, exactly, the coupled one has basically the advantages of both. The only downside is if the static tool has the false negatives, maybe because of unsupported feature, then the dynamic tool or the coupled one will also forward it. But we also have some research tackling this, but yeah, this will be published later this year, I think. Okay, I'll skip over that. So I think the last 2 slides. So I also want to talk about related dialects. So basically we have in MLI lots of dialects, not upstream there are quite a few, but also lots of not upstream. So for example, there's the MPI dialect. I think there's also quite often a question why you just don't use the MPI dialect or something. First of all, when I started my project, there was no MPI dialect. Secondly, the MPI dialect from its scope has no frontend or backend. It just defines the dialect, which should adhere to the MPI specification. But we have a different target. We want to have a unified layer, and yeah. And if you look at the MPI deck upstream, it's really small. It's only covers a really small percentage of MPI. So right now we have a bigger coverage. And of course, we also want to use different dialects, different program models. However, we could use dialects such as the MPI dialect, or there's also right now an OpenSHMEM dialect, I think recently added. We could use them as an intermediate step. So basically LLVM IR, or getting to MLIR, and then converting, transforming the function calls from different program models first to its specific dialect, and then going from the specific dialect to the general dialect. This could be a valid approach. There's an OpenMP dialect where we will look at later an extension. then I just listed here some related dialects. There's the async dialect, which has asynchronous and runtime behavior. We have different abstract dialects. So in MLR, it's quite common to have like an abstracting dialect. For example, there's a GPU dialect. And the GPU dialect abstracts over, for example, OpenACC, OpenMP, AMD GPU, NVGPU dialects. And here are other dialects which I grouped. So my lessons learned or current challenges, I hope they may lead to some discussions later on. So currently I'm working on porting existing analyze, which I maybe wrote some years ago when I was like really new into all the compiler stuff, to MLI's data flow framework. LLMs are quite helpful actually, especially as a like solo developer. I also switched recently from a CMake build system to Bazel because I used like this enzyme project for the front end, and they have lots of dependencies, and trying to mix CMake with another Bazel dependency and so on and so forth was really difficult, and also giving my students, okay, please build this like this, and this is really difficult. And after switching everything to Bazel, it was a bit hard, but right now it's really convenient, just pressing one button and everything works. And one problem I had was like with generally LLVM and MLI and so on, like it's always difficult. You want to implement something and you say, okay, this really, maybe some really fundamental analysis, but you don't know if this is really implemented somewhere in the LLVM project. Yeah. Then it's a general thing that you, there are multiple ways of implementing something, and also it was really cumbersome to have like no official C++ front end. Yeah, we changed over the years lots of the pipeline, I think 3 times, and always leading to some months of implementation maybe. There's like this MLR-based Clang IR, but it is, I think it takes still a while until we can use it. So although, like, if I look back like 2 years since I'm working really on LLVM, like over time you accumulate certain knowledge, but I think it would have been good if I just say, okay, I spent 1 week only looking at LLVM project, which libraries are implemented and so on. Maybe this would this help me in the long term. And it's also really helpful to be as close to main LLVM, because I also realized, for example, like some weeks ago, I wanted to feature X, and that would be quite cool. And just looked, it was added like 1 or 2 weeks ago. And if I would be like some months behind LLVM main, I could not use it, basically. Yeah. And I think getting feedback, also code reviews are quite important, which was a bit shorter at my side because I'm at the HPC Institute and they are not really like compiler experts. And just through feedback and code reviews, you can really develop your skills, I guess. Yeah, conclusion, maybe just reading the headlines here. So we have a unified representation of parallel programming models for SPMD like program models. We have an explicit and rich representation of parallel semantics. And we enabled like a generalization and improvement of static approaches on these models. We have different use cases so far, mostly like correctness, but we will also add soon some performance optimization use cases. Yeah, and we applied it also, I didn't show it here, but we also applied our approach to proxy apps, where we also analyzed our like the runtime, so performance overhead, let's say, and except MV analysis, everything was good, and we are now like switching to the framework, like MLAS data flow framework, and getting rid of certain limitations. So I think we already have solved this, but I don't have new results to show you. But yeah, I'm quite confident that it will. So finally, if you have any suggestions about the shortcomings, you are welcome. Thank you.
And thank you, Semih. That was really nice, really interesting. Is there any questions from the audience, maybe? We can take a couple of them. Yeah, I can just give it to you.
Thanks. So very cool. This reminded me a lot of this paper I read recently about lint queue. I don't know, are you aware of this? So this is, I guess in quantum computing, they have sort of the same problem. There's a bunch of different quantum computing dialects that you use in Python usually. And they built this linter, so it's a bit less powerful than what you're doing, I guess. But they have this same model of taking all the different quantum programming concepts, abstracting these models over to this, and then they implement lints on that concept, so they can do the same kind of checking. But yeah, very cool.
Yeah, thank you very much.
I'm wondering, so you have these 4 different programming types, or these models of computation that you accept in your unification. What is it like to add a new one, especially if it's not so compliant with the abstractions that you've had before?
That's a good question. It depends, actually. I mean, at some point in the abstraction, you always lose some information. Sometimes you say, okay, I use here some information, some details, but you always need to make sure that you don't lose correctness. So, yeah, you need to have this in the background. For example, like in the current 4 program models, like MPI, SPMD, nickel, and VSHMEM, nickel is kind of similar to MPI, but has some certain differences. So it's like for the GPU communication, and VSHMEM is like an implementation, like a GPU implementation of OpenSHMEM. Yeah, and also I need to admit that my dialect is mostly focused on MPI, which is like currently the standard for stuff. Yeah, so it's not, I would say, if it's completely different, it might get a bit difficult. Or you would end up in introducing new operations, basically. So you would make the layout bigger, which is a bit contradictory to your like aim of unifying stuff. But yeah, this could be last resort, let's say. Yeah.
All right, thank you.
Thanks for the talk also from my side. I have kind of a follow-up question to this one. What's the kind of core semantic intersection of these target models, MPI and these guys, that you're actually exploiting in SPMD IR? So what are the kind of the common features that you require from these models, and what kind of features you may exclude?
Yeah, good question. So I think I can go somewhere here. The common features are, I think, here visible. So, like, nearly all program models have like management functionality, like API. And first of all, they're all API, like function call based, yeah. And there are, for example, functions for process and device management. They say, okay, please give me the process ID, or create me a communicator, or allocate special memory which I can use in my program model. And then they all define certain communication operations. For example, they all define point-to-point, like send, receive, broadcast. This is like really common. And yeah, the difference are more like really how they are synchronizing stuff. And there are some objects in the, let's say, in the program models. For example, like what I call like a request handler window. They are like more like a means for the program model. They are not like really the how do you call it, like first design goal. So yeah, and what I'm using is that, and yeah, okay, maybe this is the right answer. So the basic is like the biggest overlap is really the SPMD part. So SPMD stands, maybe I should say it, single program multiple data. So which assumes you have one program, but this program is executed by all the processes. And you mostly, if you want to give one process a different task, you would say, give me your ID, and if the ID is 5, let's say, do this. Or if this ID is X, do this. So the execution model is same. And if you want to communicate data, then you would use the functionalities in the programming model. Yeah, I don't know if this answers the question a bit.
Kind of, maybe one.
Yeah.
So you don't just support rows where you have the check mark in each column, right? So you also support like send receive, which is, for example, not
the
supported.
check marks, sorry, maybe I should say, like the check marks is not about supporting on my side, it's more about if this program mode is supporting this feature.
Exactly, but for example, if you have a send receive, it's supported by MPI, but not by SPMM.
Exactly, I don't have...
But you supported in SPMD IR,
Yeah,
right?
yeah.
So this send that you kind of have taken from MPI, it's seamlessly composed with maybe SPMM concepts that you also have in SPMD IR? Because it's kind of a distinct feature of MPI of MPI and Nickel.
Yeah.
Here, but you also can compose it with the building blocks from SPMM that you have in SPMDIR. Do I get it right?
Yeah. So basically, yeah, exactly. So if you have a starting, like if you have a program and want to get it to the SPMDIR, then yeah, in MPI you have point-to-point, so you can create like a send operation in my dialect. And in SPMM you don't have point-to-point, you have like this one-sided communication, like a put and get. And then you would create that. The only thing you can't do is, let's say you want to lower this like to machine code again. Then you would need to, and then you have, let's say, a send. And once you get back this to, let's say you want to get this to SPMM, there is no SPMM send in SPMM. You can't do that. So yeah, so you would need to lower this to MPI, for example.
Okay, I see. One last one, so very high level question. So this SPMDR, is it kind of an alternative to MPI and SPMM? So you see it as kind of a replacement for them, or is it kind of...
No, it's not a replacement. It's just an abstraction on compiler level. So if you want to have runnable code again, then you would need to tell the compiler, please go back to the initial program model, or say, I want to start in MPI, but want to get to Nickel because I want to have device support, for example. So you would need to tell him, and then he can try to get to a different program model. Like getting back is probably like simpler, it's easier. But getting from one program model to the other is maybe even impossible in certain cases, and maybe possible in other cases.
But this means you could basically convert between like MPI and Nickel if they have, like if the program has features that both support, right? Like,
yeah.
Did you think about doing that in your framework?
Yeah, actually, I also have some like master thesis doing this right now. So yeah, he's just elaborating what is possible basically, where are the limits on doing this. I think there are research like even 20 years ago trying to get one program to the other, and yeah, it's probably impossible to get an arbitrary program from one into the other, but it would be really cool to see if I can get like really like proxy apps and so on from one program to the other, and so on and so forth. And especially getting, for example, MPI to Nickel and so on is quite interesting because yeah, nowadays everyone goes to GPU at least, wants to have speed ups, and then if you can do this, you can say, okay, do this, and then you may end up with really good speed ups.
And I think the like semantic information is also super powerful for performance optimization, right? So if you think you could like do that code analysis for like communication, right? So you have like on some loop iterations, you have a halo exchange, which is dead code. So you can just get rid of the communication between the devices and theoretically get big speedups, I would guess. Have you looked at that at all, or seen other interesting performance optimizations that are like relevant between devices?
Between devices. So far I looked at the correctness stuff, and right now, like this last month, I spent to make everything more mature and getting, like, for my prototype implementation, a bit better implementations. And the next big milestone would be have performance optimizations. And for example, one optimization use case I chose was, let's say you have one device wanting to communicate with the other, and it could happen because the program model does not support it, that the device is first communicating to the CPU, and the CPU is communicating this to the other CPU, and this is just communicating back to the GPU instead of GPU-GPU communication. And if we can see this and optimize this, you could replace this by direct GPU-to-GPU communication and would reduce the overhead there. This would be one.
Cool, really cool, thank you.
I'm
afraid we're a bit out of time for the presentation questions, but to Semih and to Martin as well with regards to further questions. Afraid we might need to go ahead with the next part. Let's please, thanks.
Yeah, thank you very much.